Hello all. For my final project, I focused on optimal feed-forward neural network regressor design. I investigated input preprocessing, different hidden layer activations for the single node output layer, and appropriate cost functions. I also researched adaptive learning algorithms as alternatives to stochastic gradient descent. Finally, I'll discuss an alternative to grid search for obtaining an optimal network structure design. A number of considerations need to be made when designing a neural net regressor as compared to a classifier. First, and as it might pertain to classifiers as well, having a data set with mixed types and drastically different scales required creating dummy codes for the categorical data and normalizing the continuous variables. For my data set of choice, this proved to have a drastic effect on the performance of the trained network on training, validation, and test data sets. Next, sigmoidal activations did not make sense for a continuous prediction model, so simple linear and ReLU activations were compared for both the hidden and output layers. The output layer is especially different in a regressor compared to a classifier. Because a single continuous value is being predicted, the output layer has a single node that aggregates the last hidden layer activations. Aggregation methods can differ. One method, as illustrated, is to simply sum the activations from the last hidden layer. Finally, the cost function must be appropriate for continuous output. Mean squared error or mean absolute error candidates. I focused on mean squared error for its application of prediction confidence. In this course, we discussed stochastic gradient descent as a neural network learning algorithm. It is heavily reliant on hyperparameter selection, especially with regards to the learning rate. ADAM, standing for adaptive moment estimation, is an alternative to stochastic gradient descent. ADAM is a gradient descent optimization algorithm that computes adaptive learning rates as opposed to static for each parameter. Also, unlike stochastic gradient descent, it has a momentum calculation built in. In addition to storing an exponentially decaying average of past squared gradients, similar to the ADA-delta or ARMS prop learning algorithms shown in the GIFs, ADAM also keeps an exponentially decaying average of past gradients, similar to momentum. According to Stanford's Neural Networks course, quote, "In practice, ADAM is currently recommended as the default algorithm to use, and often works slightly better than ARMS prop. As seen in the GIFs to the right, ARMS prop greatly outperforms stochastic gradient descent and stochastic gradient descent with momentum, and comparably to other adaptive learning algorithms in avoiding stagnation in saddle points and, most importantly, quickly reaching absolute minimums." A major interest of mine is not in the programmatic implementation of neural network algorithms, but in their application. The end of Chapter 3 of Nielsen's Neural Networks and Deep Learning discusses automated techniques for hyperparameter setting. Adaptive learning algorithms can aid in many of the hyperparameter settings, so my focus was on another major part of the process, neural network structural design. One paper was referenced as containing preferred alternatives to a simple grid search, Random Search for Hyperparameter Optimization by Berkshire and Brengio. The paper found that random search is more efficient than grid search in high-dimensional spaces. The graphic shows how a traditional grid search provides even coverage of the multidimensional space but leaves large gaps on the subspaces. Applying this technique to the layer sizes and regularization factor of a deep network is advisable. Thank you.